Next, we have Elias joining us from MIT. So, talk about the method. Elias joining from MIT to talk about
Can you hear me? Sorry.
Networks via cryptographic tools.
Yeah. Hopefully you can hear me. Let's see if it seems. Just a moment. Okay. Thank you very much for the invitation, and yeah, I'm really sorry I cannot be there. So okay, so what I'm going to talk to you today about, I'm going to talk to you about the hardness of one hidden layer ReLU neural networks, and I will discuss with you a potential new approach or new angle of this problem via cryptographic tools. Okay, and whatever I'm going to say today is actually joint work with Joan Bruna and Min Jason from NYU. Okay, so let's see. So what is the topic of this talk is hopefully a clean setup. It's how hard it is to learn, as I said, in one hidden layer neural network. And what do I mean by this? Is there existing hidden weights, Sj and Tj, and some hidden weight vectors, Wj. And we're observing samples from this one hidden layer neural network that, of course, are like the neural network applied to a specific point xi plus some additive noise, and we receive n samples of them, and we assume the ambient dimension is big that goes to infinity. And I will assume that like the input is coming from a Gaussian isotropic distribution, so somehow the most innocent looking input. And for the noise, I don't assume anything at the moment. And to kind of forget about all these parameters here, I will assume that like everything depends polynomially in the ambient dimension. So like both the width and the norm of the weights are like at most polynomial in T. So somehow there is no sort of cheating or in anything of the sort in this way. Okay. And the question is potentially the natural one is like how hard is to learn this? Okay. So like if you receive polynomially many in the dimension samples, can you use this YXI and actually learn in polynomial time the hidden function, the hidden neural network function? Of course, this is a very classic question. I have not attempted doing this sort of any literature review, but just to give you an idea of where we stand, the answer is yes. Under structural assumptions, we can do this in polynomial time. For example, if the coefficients Sj are like non-negative, we can do this. Or if the weight vectors have some certain non-degeneracies, have some full rank property, we can again do this in polynomial time. Yet, it seems that even in the case where this noise is zero, there are SQ lower bounds for this model in the completely general case. Okay, so given this, like, the question is, what else is there to say? And what I want to present to you today is that actually we can say something more about the hardness of this problem, under a catch, of course. I will present to you a recent result that actually there is one hidden layer neural network of this form with polynomial width, polynomially bounded parameters, etc., which under Gaussian input and arbitrarily many polynomial dimension samples, it's provably cryptographically hard, which I will explain what it is, to learn better by chance in polynomial time. And the catch is that to get this result, which I will explain again what's cryptographically hard, we want to be able to add some very small, or some small, let's say, noise to each sample. So add an inverse polynomial in the dimension small adversarial noise. So like if I'm allowed to add a little bit of noise, like let's say d to the 100 noise on each sample, then we can prove that actually there is certain hardness in this to learn this neural network. And okay, what do you mean by cryptographically hard? So cryptographically hard is a notion I'm using a little bit vaguely here. It's with what we prove is there's a certain reduction from what is known as a worst case lattice problem, worst case shortest vector problem, or gap shortest vector problem with polynomial dimension approximation factor, worst case over lattices, which is believed, which we prove that if you're able to learn this neural network better than chance, then you will be able to find an algorithm that goes polynomial time for the worst case of the vector problem with polynomial dimension factor, which it's widely not believed in the cryptographic community to be the case. So it's like, as an assumption, it's really the base of what is known as lattice-based cryptography, and it's really believed to be even quantum resistant for polynomial time algorithms. So that's what I mean. It's not NP hard, so it's not an NP hard. It's not the worst average case reduction from NP hardness, but from, let's say, a class of problems that we really don't believe there is a polynomial time algorithm. even quantum one. Okay. The reduction, though, besides all these fancy words, is really not that hard if you see the literature and, potentially, I mean, I personally like this thing about this result, is really a simple reduction if you see the literature from a specific point of view. And it really uses these new or relatively new tools, let's say, a specific one called continuous learning with errors that appeared in the TCS community last year. And also something we coined, but really appeared in the Samir paper 2017 called cosine neuron. So by combining these two that I will try to present to you, you can actually establish this reduction. And just a comment, we're not, of course, the first one to cryptographic results about such models. And there is actually, a member of this collaboration, like Amit Danieli and his company that has like a striking number of such results, which are very nice. I want to say that it's kind of incomparable with, first of all, with what I'm saying here. The recent result by the NLN party, for example, it's based on the assumption of the existence of a local pseudorandom generator, which is kind of another cryptographic assumption, which is different than this worst case of the vector problem. And also, to my understanding, none of these results were able to handle the one hidden layer neural network and the Gaussian input. So somehow it's getting this, but on the other hand, we have always the catch of this polynomial small adversarial plots. Okay, so this is the result. Okay, let me tell you a little bit more about it. So I want to present to you a little bit of how does this reduction work, and how we're able to combine kind of some tools to construct this bad neural network, this hard neural network. Okay, so what's the cosine neuron? So the first jump is this cosine neuron. So a cosine neuron is nothing else than a generalized linear model with a small catch. So, okay, what's the cosine neuron? So there exists a certain parameter beta, which is the noise level, and a certain hidden direction W, which is on the sphere. So some hidden direction on the sphere. Okay. And what we receive in this model, we receive samples of a specific form, which as follows. At this moment, how do you generate a new sample from the cosine neuron? You sample an isotropic Gaussian, and then you project it into the direction of W. You inflate it a little bit with this square root D, so there is some polynomial dimension factor. It could be like D to the 10. Okay, but let's say square root D is the minimum that works. And then you apply the cosine activation function, and then you add a little bit of noise to it. Okay, so why this is not a classic generalized linear model is because there is this dimension-dependent, let's say, multiplicative factor inside the cosine argument. Right, so it's not the activation function is cosine square root D times T. So it's like a very oscillatory thing that the period becomes 1 over square root D. And this is very important. And what is, and of course the XIs are at most beta. And what will be the goal of the cosine neuron is to learn it. Okay, so to be able to learn besides this adversarial noise better than chance. So to be able to output some element G hat, okay, to do this agnostic learning task here, to output some G hat that's null to error from the cosine neuron with Gaussian input is better than chance, better than what would you output it with nothing, no sample at all, by constant additive factor. Okay, what does this have to do with neural networks? But hopefully the cosine neuron is clear. Okay. So, okay, what does it have to do with neural networks? So the reason, it has appeared actually in the literature already is because it has, cosine is a Lipschitz bounded function. So in particular, it can be well approximated by neural networks, one hidden layer neural networks with ReLU. In particular, it's very easy to prove that for arbitrarily polynomially many samples, I can always create some appropriate scalars Si and Ti that somehow the corresponding NR, sorry, some translation, so that the corresponding neural network with polynomial width, and of course all this will be polynomial bounded in the dimension, are really simulating the cosine neuron up to inverse polynomial nodes. So exactly because it has this continuous Lipschitz structure, it allows me to approximate with inverse polynomial error. Why this is interesting is because really, therefore, learning this neural network with adversarial noise is the same question. Polynomially small adversarial noise is the same question as learning this cosine neuron with adversarial noise. Right. So somehow, if I receive samples of this cosine neuron with polynomially small adversarial noise, it's really the same model as receiving this up to twice, let's say, the magnitude. And what is the most important thing here is the negative implication. Somehow, if I'm able now to prove a lower bound on how hard it is to learn the cosine neuron with adversarially small polynomial small noise, I will immediately get a lower bound for this one hidden layer neural network with Gaussian input with adversarial small noise. So somehow it gives you the cosine neuron, it's already giving you like some instance of the one hidden layer neural network with Gaussian input with adversarial noise that if you can prove some form of hardness. And why to even believe that this is hard is, of course, this connection has been made, and maybe not phrased in adversarial noise term, but like because of this approximability of the one hidden layer neural networks, people have studied this and proven that even if you have no noise in the cosine neuron, actually, exactly because of this oscillatory behavior translates to some appropriate flatness in the Hermite basis, gradient descent in the population risk fails for polynomially many samples, and also there is some. Okay, it's not a complete SQ, but like some Lipschitz SQ family also fails. Also, it's could be believed that's actually a hard instance here. Okay, so that's cosine neuron. What is now continuous learning with errors? What's this other tool we need? So like we know this from the literature. Now let's see this other piece from the literature. So this is a nice continuous version of the famous learning with errors in the cryptographic community that appeared last year. And what is this model? So you will see that similar to the cosine neuron in its own right. So again, there is some beta, which is a noise level, and there is W, which is the hidden direction. And then, similar to before, like we're receiving samples, and how does this sample are generated? It's like before, but a generalized model, but with a little bit more, if you want, peculiar activation function. We receive isotropic Gaussian input, Xi, then we project it on W. We inflate it by d square root d. Again, it could be d to the 10, it could be d to the 100, but you need some polynomial dimension inflation there, and you add a little bit of Gaussian noise to the output of this multiplication, and then you take the fractional part of this. Okay, so somehow like this continuous activation function. So somehow like you receive samples like this, but like you only keep the fractional part of them. And what's the goal? The goal of continuous learning with errors, because it's more of in the cryptography mindset, it's more like a detection problem, as we will call it. It's more a decision problem, as they call it, which is to detect better than random between receiving polynomially many samples of this format, as I just described you, and null samples, which are like Xi, and then just like some label, some uniform label, in where the fractional part takes place, minus half. And the goal is, can you do this with polynomial dimension samples and time? And the very nice result by Brunner, Regev, Song, and Tang from 2020 is that if you were able to do this with inverse polynomial small noise for the beta, then you would be able to solve this problem I told you, the gap SVP problem, worst case, so it's a worst case to average case reduction by a quantum polynomial time algorithm. In a regime, in polynomial the approximation factor, in a regime we don't believe that such an algorithm exists. Otherwise, what is known as lattice-based cryptography fails. Okay, so that's kind of the continuous learning theory, what we will borrow from the continuous learning theory. Okay, so there is this decision problem that's believed to be hard. And our result is essentially combining these two. So it's like, remember the cosine neuron. The cosine neuron is just cosine of this plus a little bit of noise, adversarial, but like smaller than this beta. Then our result is essentially the follows. It says that like if there exists a polynomial time algorithm now for the cosine neuron with noise beta, okay, beta, I take it for the theorem here for simplicity one we don't need it, but like for the application here, any inverse polynomial is small beta, so 1 over t to the 10. If you find a polynomial time algorithm that can solve the cosine neuron with noise beta, then you can create a polynomial time algorithm for this continuous learning with errors problem I told you with noise almost beta. And in particular, from the result of last year, there exists a quantum polynomial time algorithm for worst case gap SVP up to the polynomial dimension approximation. So connecting the dots with approximability of the cosine neuron, this is the hard distance. This is the approximation of the cosine neuron. Approximated the cosine neuron by one hidden layer neural network polynomial dimension width with isotropic Gaussian input. Nothing is peculiar in the input, adversarial noise is with hard. And and why cosine is it was used, how it was used, right? So what you need is essentially periodicity and Lipschitzness. If you have these two tools, you can connect CLW with the neural networks. Like you need something that I will explain more into this. So like any periodic and Lipschitz function really works here. And just like a super quick comment on the proof, like just some intuition, how do you connect from cosine neuron to CLWE? Well, it's a very simple idea hiding behind. If you give me a CLWE sample, which is, it's of this form, right? So it's of this form, it's the fractional part of the projection of xi to w plus a little bit of noise. I can create a cosine sample with almost the same noise. And the reason is, cosine doesn't care about the integer part. So it's already a periodic function. So exactly because it doesn't care about the periodic part, if you apply the cosine to pi zi here to the label of the CLW sample, it's really the cosine of the actual argument without the mod 1. So because of this, this is just cosine of this plus this, and because of the ellipsisness, you get some junk here, some like it's the cosine of the projection, there's a little bit of noise, and that's the max of Gaussians. Okay, so like this is just to give you some intuition of like how do you transform like CLW samples cosine neurons, and then you use your favorite, your polynomial for cosine neuron to solve it and carry the reduction. Of course, details aside, but like hopefully this gives some intuition of the simple idea behind. And that's the result. Again, it's this reduction to worst case SVP. And just to wrap this up, let's make just a few comments. Somebody can ask, okay, but like you just told us that like gradients and SQ do not require this beta, do not require this inverse polynomial additive noise to be hard. They still fail. It turns out that the cosine neuron does not actually though have like this behavior, like to the extent there is a completely other computational statistical gap and a completely other phase diagram of the hardness of it, that if beta is actually small, there is some polynomial time algorithm that works, even if gradient descent and SQ still fail, which is based on the Lertra-Stralovas algorithm procedure. So somehow it is crucial to have inverse polynomial noise to be able to establish such a worst case hardness result. Okay, this is just to tease you if you want to look in the paper for some other part. And finally, this is really what I want to communicate. This CLW hardness is actually interesting. It's really ML relevant, and it gives, for example, like as a I think a relatively simple argument gives like this lower bound. So yeah, thank you.
Thank you, Ilias. Questions?
Is this diagram of hardness on the noise specifically for the adversarial noise, or does one expect this for like label flipping noise or something a bit less?
Yeah. So okay, so this is for the cosine neuron only, right? Yeah, and okay, a positive result for adversarial noise is stronger, of course, than everything. So like somehow the positive result here is for adversarial noise, and in particular implies for any favorite noise you may have, but it's like has a variance which is appropriate. And the crypto hard here, we needed for technical reason adversarial result, but really like some position specific random noise suffice. But somehow the noise we add kind of depends on the specific relation of xi and w. So like it ends up requiring the variance of it at least. It's a Gaussian noise if you want. It's approximated well by Gaussian noise, but like the variance depends on the specific instance. So like I don't know if you can go to random noise statistically, but I wouldn't be super surprised if there is some random noise version of this result.
Well, thank you.
Yeah, sure.
Other questions? If not, we thank Ilias again.
Thank you very much.
And yeah, so perhaps we take a short break.